Using fire to make ice? I know, it sounds like a paradox, right? But it's not some kind of magic trick. It's actually an incredibly clever piece of science, and today we're going to break down exactly how it works.
So let's just jump right in with the big question. Can you really make ice with fire? I mean, it seems to defy the basic laws of nature. But the answer, you'll see, isn't magic, it's just some very, very clever physics. Let's get into it.
But to really get how this wild idea works, we first have to take a quick look at the technology we all know and use every single day. Yep, I'm talking about the standard refrigerator, the one that's probably humming away in your kitchen right now.
Think about it. The machine in your kitchen, your car's AC, pretty much every commercial cooler you can think of, they all use a system called vapor compression refrigeration. It's the king of cooling technology, and its most important part is a mechanical pump called a compressor.
So this is basically what's happening inside your fridge 24/7. It all starts with that familiar hum you hear. That's the compressor. Its job is to squeeze a refrigerant gas, which makes it super hot and high pressure. That heat gets dumped out the back of the fridge. But then the real magic happens. An expansion valve lets the pressure suddenly drop, which makes the refrigerant intensely cold. And that cold liquid is what soaks up all the heat from inside your fridge. The key takeaway here? It's all driven by that noisy electric compressor doing all the heavy lifting.
Okay, but what if you could get that same cooling effect, but without that big, clunky mechanical compressor? Well, that's exactly where the vapor absorption cycle comes in. It's a totally different approach that swaps out mechanical energy for thermal energy. In other words, you power it with heat.
Okay, I know. At first glance, this looks a little complicated, but trust me, this is the entire heat-powered refrigeration cycle all in one picture. It's a clever, self-contained loop that can work without a single mechanical pump. Let's walk through it step by step and see how it all fits together. Our journey starts right here with absorption. In this system, you've got two key fluids working together, a refrigerant, like ammonia, and an absorbent, maybe something like water. The easiest way to think about it is that the water acts like a sponge. In this part of the system, the water soaks up the low-pressure ammonia gas, creating this concentrated ammonia-water solution. All right, now for the really clever part. That solution gets moved over to a chamber we call the generator. And this is where we add our heat source. It could be a small gas flame or even waste heat from a factory. This heat boils the ammonia out of the water, creating a high-pressure ammonia vapor. And here is the absolute key. The heat we're adding right here is doing the exact same job as that noisy mechanical compressor in a normal fridge. It creates the high-pressure gas, but it does it without a single moving part. From this point on, the cycle starts to look a lot more familiar. This hot, high-pressure ammonia vapor travels to the condenser, and just like on the back of your fridge at home, it releases its heat into the outside air, cools down, and turns back into a high-pressure liquid. And finally, this is where we actually get the cooling. The high-pressure liquid ammonia flows into the evaporator. This is the part that's inside the cold box. As it expands and evaporates, it absorbs a ton of heat from its surroundings, which is what makes the inside of the refrigerator cold. That ammonia is now a low-pressure gas again, all ready to be soaked up by the water and start the cycle all over again. The loop is complete.
So there you have it. Two totally different paths to get to the exact same result, making things cold. Let's put them side by side to really highlight what makes this absorption cycle so different and, honestly, so special.
This table really lays it all out, doesn't it? The biggest difference, right off the bat, is the energy source. Your standard fridge needs electricity to do mechanical work, while an absorption fridge just needs raw heat. And that leads directly to the next huge point, moving parts. A standard fridge has that humming compressor and fans, while an absorption fridge can be built with very few or even zero moving parts. And that has some massive advantages. Now you might be thinking, okay, that's a pretty neat physics trick, but so what? Why does this matter today? Well, it turns out this idea, which is almost 100 years old, might just be a key part of our energy-efficient future. Let's see why. The advantages are pretty huge. I mean, just imagine capturing all the waste heat pouring out of a factory or a giant data center and using it to power a massive cooling system for practically free. And because there's no compressor, these things are incredibly reliable and completely silent. This makes them perfect for off-grid homes, RVs, or even remote medical clinics, where electricity is hard to come by, but a simple heat source like propane is easy to get. And if you thought this technology couldn't get any cooler, well, get ready for this. The pumpless version we've been looking at wasn't invented by just any engineer. It was co-invented way back in 1926 by Albert Einstein and his student Leo Szilard. They actually wanted to create a safer refrigerator after hearing about a family that was poisoned by a leaky conventional fridge. Their brilliant solution was a design with no moving parts and no seals that could ever fail.
So, that leaves us with a fascinating question to chew on. In a world that's desperately searching for sustainable energy solutions, could the future of cooling actually be this silent, elegant invention from nearly a century ago? It's definitely something to think about.